Hi guys, welcome to Sigma Maths. This is the fourth video in a series of videos looking at the exponentials and logarithms part of the A-level. In this video we're going to be going through the practice questions that I set you at the end of the last video. If you have not yet had a chance to watch the last video and you haven't yet seen these questions, then I strongly suggest that each time a question comes up you pause the video before I start going through it and have a good go at it yourself. Okay, so let's have a look at question 1. This question requires us to write down the value of a selection of log expressions, starting with part A. Okay, so if we think back to the last video and what we know about logs, log base 4 of 16 basically asks us, what power of 4 gives us 16? So that's fairly straightforward. We know the answer is 2 because 4 squared equals 16, but I also just want to show you how to approach this question by writing a log equation as an exponential equation. So if I turn this expression into an equation by introducing the variable x being the number we're trying to find, our unknown. So x equals log base 4 of 16. Then we can simply write this as an exponential equation in order to solve it. Now we know our base number is 4, so that would be our starting point. The power is what's on the other side of the equal sign, so 4 to the x equals 16. Now the reason I wanted to show you this method is because for some of you, when it's not clear what power of 4 would give 16, or maybe that just doesn't quite make sense to you, then you can rely on this method where you turn it into an exponential equation, which is a lot more familiar because you have done exponential work in the GCSE, but you have not seen logs prior to the A-level. So from here, it is very clear that we are doing 4 to the something equals 16. We know that 16 can be written as 4 squared, therefore we have x equals 2. Okay, let's take a similar approach for the next one. So we'll use x again. X equals log base 3 of 1 over 27. So again, base number, the little number by the log, 3 raised to a power we do not know, x, equals 1 over 27. Now we can focus on the 1 over 27 and think, okay, how can we rewrite this as a power of 3? 27 is 3 cubed. To get rid of the reciprocal, we would need to introduce a negative power, so 3 to the negative 3. Then we can just compare the powers, seeing as the base number is the same, and get x equals negative 3. Okay, part C. Again, x equals log of 0.5, log base 0.5 of 2. So 0.5 is our base number. I much prefer to work in fractions, particularly when I'm doing exponentials and logs. So I'm going to write that as a half, all raised to the power of x, equals 2. Now a half, we know, can be written as 2 to the negative 1. So that's 2 to the negative 1 raised to the power of x equals 2. If we use the power to a power rule of multiplication, then we have 2 to the negative x equals 2 to the, remember this is a 1. And comparing powers like we did in part B, we've got minus x equals 1, x equals negative 1. And finally, part D. Now, I'm going to go through it in the same way as the last ones, but this one I'm just going to point out in a moment. Should be quite easy just to look at and know. Okay, so here we go. B being the base number, to what power gives us the square root of b. The square root of b can be written as a power of a half, and comparing coefficients, that gives us x is 1/2. So it's not necessary to do all of the method I've just done. You could just simply spot that the root can be written as a power of a half, and as this says, what power of b gives me b to the half? The answer is clearly a half. We could also use one of our log laws here and bring the power down in front, so a half log base b of b. And then we also remember one of our other log laws was we saw it as log base a of a is 1, because b to the power of 1 gives b. So that would just become 1, and then we would just get the half. Okay, so there's a few different ways that we can get to the answer. But I wanted to show you the way that links back to the exponential equations that we've seen before. All right, let's move on to question 2. Okay, we've got 2 questions on here. Without using a calculator, justify why log base 3 of 45 must lie between 3 and 4. We really do not need our calculators for this. So the way we're going to do this is we're going to use numbers inside the log that are powers of 3, that are known powers of 3. So straight away we're thinking we're working in base 3. So the kind of numbers we're thinking about are 9, 27, 81. So this is 3 squared, 3 cubed, 3 to the 4. Okay, so our number 45 lies in between 27 and 81. So we can say that log base 3 of 45 sits in between log base 3 of 27 and log base 3 of 81. Remember, we're absolutely fine saying this because our log graph is increasing and continuous. So just a little reminder for you, our log graph looks something like this, going through 1. Okay. And seeing as we actually know the value of log base 3 of 27 and log base 3 of 81, because we chose them because they are powers of 3, we can replace this one with 3, because 3 is the power that turns 3 to 27. There we go. And log base 3 of 81, what power of 3 gives us 81? 4. And we are finished, because we have shown that log base 3 of 45 lies between 3 and 4, and we have very clearly done this without our calculators. Good. Okay, question 3. Okay, this is a fairly easy one, because this is just making sure that we remember our laws. Log base a of a on its own does just have a power of 1. What power of a gives us a? 1. Part B, log base a of 1. Okay, well, what power of a gives us 1? We know that anything to the power of 0 is 1, therefore the answer to that is just 0. Excellent. Okay, question 4. We've got 3 parts to this question. Write each of the following as a single log and simplify. So this is entirely using our log laws to bring this all together and write as the smallest log term that we possibly can. So let's have a look. Now they're both base 10, which is promising because we would not be able to combine them if they were not the same base. We do have numbers in front though, so we're probably going to want to deal with these first so that we can use our addition law to combine them. So we remember that having a number outside the front of a log, multiplying the log, that will go in as a power inside the log. So log base 10 of 5 squared would be the first term. The second term would become log base 10 of 2 squared. So make sure we show all of our steps. That would be 25. And this would be log base 10 of 4. Remember, if we add our logarithms together, as long as they are the same base, it means we can combine it into one log and multiply inside the log. So that becomes log base 10 of 25 times 4, which is log base 10 of 100. What power of 10 gives us 100? Happens to be a nice one, so we should definitely evaluate it. 2, because 10 squared is 100. Alright, part B. Log base 4 of 90 minus log base 4 of 26. Okay, so subtraction in a log, or subtraction between logs, sorry, results in a division inside the log. That's one of our laws. So we get log base 4 of 90 over 26. And with that, all we can really do is simplify down to 45 over 13. There's nothing more we can do there because 13 is a prime number. So don't be put off by the fact that it was a very short piece of simplification. What I do actually think this question was trying to trick you into was doing 90 take away 26, because that would leave us with 64, which is a very nice power for log base, was a very nice number for log base 4, because 4 cubed is 64. So that would lead you to think you were doing the right thing. So it's kind of one of those sneaky questions, but really just as simple as a fraction that needed simplifying. Okay, part C, we've got numbers outside of the logs again, so I always suggest that you take numbers outside of the logs inside to raise them as powers, and it also then means that you are free to put your logs together. So log base A of 100 to the power of a half, that was the number out the front there, minus, in brackets, so log base 8 of 5 minus log base 8 of 8. So that's going to be, as a single log term, 5 divided by 8. So log base 8 of 5 over 8. Okay, so we've got log base 8 of square root of 100, 10, minus log base 8, 5 over 8. Another subtraction, which means we have another division. So log base 8 of 10 divided by 5/8. So let's just deal with that quickly over here. 10 divided by 5/8 is 10 multiplied by 8 over 5. 10 and 5 cancel to give us 16. Now, please do write down your calculations if you even struggle for a moment to do them in your head. There is no shame in writing down your fraction calculations to the side of your working. Please do not think that you have to do things in your head just because you're working at A-level maths. Still worth noting it down to make sure you get it right. So log base 8 of 16. Don't fall into the trap of thinking, oh, 8 doubled is 16, therefore the answer is 2. We are working in powers here, so we need to link base 8 with 16. What power of 8 gives us 16? Well, we have to link these together into the same base number. So 4 comes into your mind, possibly, because it goes into both 8 and 16, but you cannot raise 4 to an integer power to get 8, so actually 2 is the base number we're going to want to use here. So 2 cubed to the x equals 2 to the 4. So we have 2 to the 3x equals 2 to the 4. So equating our indices, we get x is 4 over 3. So 4/3. And just to check, that would make sense because 8 to the power of 4 over 3 would be do the cube root of 8 first, which brings us down to 2, and then raise it to the power of 4, which brings us back up to 16. And there we go. All right, onwards. Question 5. Given y is log base a of 8, express each of the following in terms of y. So we are manipulating these terms so that they are in some way expressions of log base a of 8, which we will then replace with the letter y. So straight away, we're thinking, how does 64 relate to 8? This is a nice one, because 64 is 8 squared. And if we write it like that, and remember that we can use the bring down the power log law, then we quickly arrive at that. And if we replace the log base a of 8 with y, we get 2y. Okay, part B. Log base a of 2. Okay, so we need to relate 2 to 8. They are related again, but this time by a root. So we could rewrite this as log base a of 8 to the power of 1/3, because 2 is the cube root of 8. Again, the third comes down, and we get 1/3 y. All right, part C. Okay, so log base a of 16 over 1. Well, really, we can simplify that straight away and just say, well, it's just log base a of 16. The over 1 doesn't change the 16, so, we don't need to do it separately. We could do a subtraction, and then we do log base a of 16 minus log base a of 1, but then we will quickly realise that log base a of 1, as we've seen in the previous question, is just 0. So that would just leave us with log base a of 16 anyway. So again, we're trying to write 16 as a power of 8. I think we had this in the last question. The first thing we'd have to do is go down to a lower base number that we could then move up to the 16 with. So we're going to bring 8 down to 2. So I have to cube root first. And then we would need to get back up to 16, which would mean raising it to the power of 4. So it's 8 to the power of 4 over 3. So that 4/3 can then come down to the front, and we can replace our log base a of 8 with y. And we are finished. Okay, part D. Log base a of 4a cubed. Right, we're being very careful here because it might be tempting to deal with that cubed first, but that is not applied to the 4 because we do not have brackets showing that it's also applied to the 4. So we're going to want to split apart these using the log law of multiplication inside the log equals addition outside. Okay, so log base a of 4, again we've got to use 8 to get to 4, much like we did with the 16. So we can start by bringing it down to 2, so again that's cube rooting, but then we've only got to get up to 4, so that's squaring. And then we can bring the power down here, log base a of a. Okay, dealing with this one first, 2/3 will come down, leaving log base a of 8, which we will replace with y. And then here, remembering that log base a of a, that just equals 1. What power of a gives us a? 1 plus 3. There we go, we have our expressions in y. Okay, next question. Here we go. Right, we're on to solving some log equations. So straight away we're going to need some log laws for this one. Log base 5 of 10 plus log base 5 of x. They're both the same base, so we can combine them, and we know that we are multiplying inside the log when there's addition outside. So we get to this point. Now, the aim really is to get to a single log term with nothing in front, because then we can rewrite the equation in exponential form. So now we're going to go, okay, base number is 5. The power is the number on the other side of the equal sign, 5 cubed equals 10x. So here it's like, what power of 5 gives us 10x? The answer is 3. So 5 to the power of 3 equals 10x. Well, we're going to be done very quickly here because 125 equals 10x must mean our final answer, dividing both sides by 10, is 12.5. Okay, question 7. Okay, so we've got 2 outside the log. Straight away that can go in, because remember our aim is to get as close to a single log term as possible without anything in front, equals number, so that we can turn it into exponential form. Log base 3 of 2. We're going to want to bring our log terms together on one side of the equation. So I'm going to bring the log base 3 of 2 over, and I'm going to move the 5 to the other side. This is a subtraction, so we can do our division. X squared over 2 equals 5. And now we turn to an exponential equation. So base number 3 power is 5. That must equal x squared over 2. And then x equals, okay, 3 to the power of 5. We should already know 3 to the power of 4, 81. Multiplying by another 3, 243. We're going to double that as well. So that's going to be 486 for x squared. And then x will be the square root of 486. Okay, and we obviously need to simplify that square root, and we could have saved ourselves some work here actually if we had left it as 81 times 3, knowing that we had to square root, so keeping that square number factor visible. So this is actually 81 times the 3 and then the 2, so 6, and that allows us to see that this is 9 root 6. Now in this case it cannot be the negative value of 9 root 6, because we need to look back at the question, and if you remember, again, I'll just quickly pop it up here, the log graph, roughly, is not defined for negative x values. So we cannot have a negative answer here because it would need to be able to go back in to the log base 3 of x in the question. So it's just 9 root 6 is our answer. Okay. Question 8. Alright, okay, so having a look at this one. It's going to be another quadratic like the last one. We're going to get a squared in there, so we're going to need to remember to think carefully about our answers and make sure they are both valid. So we're going to start then by taking in that coefficient, log base 6 of x squared, and let's bring it all over to one side, log base 6. Oh, actually no, let's leave the log base 6 of 5 where it is. Because if we write the left hand side as a single log by dividing, so x squared over 2x minus 5, then we've got a nice setup here where both sides of our equations are single log base 6 terms with nothing in front. So if we raise both sides to the power of 6, or into the power of 6, to cancel out the logs, then we will just get what sits inside the log. So it's almost like the logs just cancel on both sides. So we just get x squared over 2x minus 5 equals 5. And now we're just dealing with a nice quadratic. So x squared minus 10x plus 25 equals 0. And having a look at this, we are multiplying to make 25, adding to make minus 10. So that is x minus 5, x minus 5. Perfect square, x minus 5 squared. So we've got that single repeated root of 5. There are no negative solutions to worry about. We are done. Okay, next one. Keep it moving. Okay, given that t equals ln x, write the following in terms of t. A, ln of root x. Okay, we're getting pretty good at this now, so we know that this can be written as ln of x to the half, which is a half ln x, which is just a half t. Part B, we're going to split apart that multiplication with addition. We're going to bring the power down. We're going to replace ln x with t, and we're going to remember that ln is log base e. Okay, and log base e of e, that would just be 1, so it would just be a2. Now they're setting us up here because in the last part of the question we are solving an equation that contains the two terms that we've just seen, which means we're not going to have to deal with them again. We can simply use our substitution of t equals ln x and turn this equation into an equation in t. So the ln root x became a half t, and the ln e squared x became 2 plus t. And solving this, take 2 from both sides, 3, take a half t from both sides, we get a half t, double both sides, and we get 6. Very good. Okay. And now we have got simultaneous equations. Okay, so first we notice that our second equation is just as standard, so we're going to want to focus on the first equation to get that written as a hopefully linear equation, although we shall see, and then we can use our normal substitution method and deal with the algebra as we would have before we even knew anything about logs. So on the left hand side we've got an addition again, both the same base, so we are allowed to make that a multiplication inside, log base 5 of 3x, and on the other side we're going to need to take the square root up in, or the power of a half, sorry, up inside the log. There we go. Again, we've got the situation where we've got a single log term on both sides, so we can just take what's inside the log, 3x equals y to the half. Alright, so we could either subtract in for the 3x in the other equation, which seems like a reasonable thing to do. We could make life a little bit easier for ourselves and square both sides here. So we get 9x squared equals y. I think that would be a bit nicer to deal with than dealing with the powers of a half. So we come back over here to equation 2, so that we're keeping things clear in our working. 3x plus y, which is 9x squared from our other equation. And this gives us a nice quadratic in x. Lovely. Okay, so this is the type of quadratic that I would suggest using the AC method for. Now that requires us, I'm just going to do this over here so you can see what I'm doing. Adding to make 3 like we normally would, multiplying to make negative 180. That's 9 times minus 20. So we need to find two numbers that are fairly close together that multiply to make minus 180. And obviously you guys can just use your calculators, but you know, hopefully by now you know my feelings. We should always try and do as much as we can without our calculators. So if you're trying to think of other factor pairs, I would maybe take the AC that we started with to get you going. So we know that 9 times 20 works, which means 18 times 10 works. We can do things, we can keep halving and doubling. So 36 times 5, 3 goes into 36. So we could divide, there we go, 12 and 15. We got ourselves to two numbers that were 3 apart. So that's going to be 15 and negative 12. So what we can do here, if you haven't seen this before, the AC method, I call it the AC method because it reminds us that we have to multiply to make AC rather than just C. What we do here is we split the middle term, so we keep our 9x squared, and then we say, well, 15x minus 12x, so we're just replacing the plus 3x there with 15x minus 12x minus 20. We then cut the quadratic in half and fully factorize each side, so 3x comes out, 3x plus 5, single bracket factorization. We know that we're expecting to get exactly the same bracket over here if everything's actually working. So just check this works. Yep, minus 4 comes out. So we get a 3x minus 4 and a 3x plus 5. So that brings us to two solutions. Either x is 4/3 or x is negative 5 over 3. But because we are working with log equations, we go, hold on, we just need to check back to the original equation. Can x be negative? No, because we have just a log base 5x term, and there's nothing there that's stopping the x from being negative when it's substituted in, so we cannot have that. So really we just have the x equals 4 over 3, which means we can also write down our y. Do not forget that we have a y value to find as well. So 9 times 16 over 9 cancel to make 16. Okay, so we've got our answers of 4/3 and 16 for these simultaneous equations because we are ignoring this solution. Okay, okay, we've got two exponential equations to solve here. We've been solving log ones up to this point. And remember, in the last video we looked at two different ways of solving these. I will solve them in the two different ways because question 11 is quite nicely suited to jumping straight into a log equation. So this would be, if we rewrote this, log base 7 of 12 equals 2x plus 4. And then this just requires undoing the plus 4 and the timesing by 2 with the x. So that would be log base 7. I'm going to use brackets here just to make it clear that my minus 4 is not part of the log, divided by 2. Now, it is very likely that the question is asking for exact solutions. I haven't written it in here, but I would always assume that we take exact solutions. Unless the question says give you answers to 2 decimal places, it is always acceptable to leave your answers in terms of logs. And it is actually quite rare for the exam questions to ask you to write down your answer as a decimal. So we're fine leaving it like that. Okay, question 12. I'm not actually going to use base 2 or base 3 because we've got obviously two different bases here. So this time I'm going to use the method where we apply a log of a more commonly used base to both sides. So we have a choice. We can either use log, which is log base 10, or ln, which is log base e. I've mentioned before, I prefer ln because on my calculator there is a button just for ln, whereas for log base 10 I would have to type in 10. So let's jump in with ln. You can use whatever you would like. 2 to the 3y minus 2 and ln 3 to the 2y plus 5. Okay, so applying ln to both sides, what that allows us to do is bring our powers down, ln 2, which means that we now have our y terms appearing as just normal linear terms, ln 3, rather than being stuck up in that power. Okay, so 3y ln 2, remember I mentioned before, I like to keep my lns on the end of the term, so there's no confusion what's inside the log. 2y ln 3 plus 5 ln 3. Okay, we need to collect our y terms together. Always think about what you're aiming for in these questions. So I'm going to bring the y term over from the other side, and my 5 ln 3 stays there, and my 2 ln 2 joins it because it does not have a y in it. Don't forget, at this point we factorize to get the y outside and on its own, as that's what we're aiming to solve for. So we get 3 ln 2 minus 2 ln 3 inside the brackets still equals 5 ln 3 plus 2 ln 2, and then we can divide, and we have a wonderful expression which we could actually put some of these numbers together. Like we could take the 5 in, the 2 in, both the same base. We could then multiply inside, but to be honest, it would just involve a lot of, well, I'll show you. So we would end up with 3 to the 5 times 2 squared, which we could write as 4, and we could evaluate that, I suppose. And then down here we would end up with a fraction because we've got subtraction, so we'd end up with 2 cubed, which is 8, over 3 squared, which is 9, so that could just be 8 over 9. But then we can't deal with the division anyway, so actually I would probably just leave it like that. The question will specify if it wants it in a particular form, so always just check back to the question. Okay, we're almost there. I think we've got maybe 2 more questions. Right, this is a nice looking question. Now, through experience, I know what this question is going to end up as. I mean, they've laid it out reasonably nicely. It does kind of look like a quadratic. It's dealing with this 2y plus 1, I would say, is the place that people make mistakes most often. So I'm just going to focus on that term for a moment. So, oh, hold on a second. There we go. So 2 to the 2y plus 1. Let's think about what that power actually means. Addition in the power is multiplication of the base numbers. So that would be 2 to the 2y multiplied by 2 to the 1. So really what we've got here is 2 lots of 2 to the 2y. Let's keep going, breaking up this power. So multiplication in the power means that there was a power raised to another power. So we've still got our 2 outside the front. It means that we can separate out the 2 to the y with the 2y, so we get a squared. Okay, do you see how that's happened? So y times 2 would give us 2y. So we've basically pulled apart the power. And the reason we want to do that is if we now put this all back in, 2 to the y squared plus 7 lots of 2 to the y minus 15. Now that kind of feeling that it looked a bit like a quadratic, even stronger. Okay, got a squared term, linear term, number term. So now we make a substitution to make things look a lot nicer. We say, well, what if we let x equal 2 to the y? This first term would become 2x squared. Then we would have 7x minus 15 equals 0. Ah, a nice familiar quadratic. Another opportunity to use the AC method as well. So adding to make 7, B, multiplying to make AC, negative 30. 10 and 3 maybe. So 10 and minus 3, yep, that works nicely. So now we split our middle term, 10x minus 3x minus 15. Just to note, it does not matter which way around you put these terms, it will all work out the same anyway. You'll get different brackets to begin with, like the first brackets that you generate, but by the time you're finished you'll have the same 2 brackets. You have a go at it, you'll see for yourself. So we're cutting it in half here. So we take 2x out, x plus 5. We're expecting to get x plus 5 over here if we've done everything correctly so far. And yes, we can take a negative 3 out and that all works. So we've got 2x minus 3 and x plus 5 equals 0. One solution, 3 over 2, and another solution of negative 5. It was an exponential equation, so we do not need to worry about negative powers. That is absolutely fine. The exponential graph, I will remind you, looks like this. So all x values are in the domain. There's no need to rule out either of those. But what we do need to remember, I'm being silly. X does not go back into this equation, does it? This is what we must not forget, guys. We've got to go back and actually find the y values, and we are going to find ourselves with a problem here. First of all, we've got 2 to the y equals 3 over 2. Okay, so we need to get y out. So we could just go into log base 2. So log of base number 3 over 2 goes inside there, and just leave it. We could have just also put ln on both sides, or applied ln to both sides, brought the power down, so that would have ended up looking like y ln 2 equals ln 3 over 2. So this is, or we could have written y equals ln 3 over 2 over ln 2. But the problem we're going to encounter here then is when we use the negative 5. So even if we just think, well, what power can we raise 2 to get negative 5? Well, it doesn't work. Well, that's going back to the log graph here. What value could we put in that gives us a negative answer? Well, there's nothing down here. There is no negative outcome for powers. That's not possible. And even if we didn't realize that yet, and we were like, oh, okay, so y equals log base 2 of negative 5. Hopefully at that point, as soon as we see a negative inside the log, we realize we cannot do it. So actually this solution does end up being a solution that we cannot include. And our final answer therefore is one of these two here. Alright. Okay, so last question of the video. Solve the simultaneous equations. E to the y plus 5 minus 9x equals 0 and y minus ln of x plus 4 equals 2. So we've got ln base e and then an exponential equation in e. So we're going to need to obviously get one equation to be the same as the other one so that we can find some way of eliminating one of the two variables. Okay, so we can either turn the first equation into a ln equation or the second equation into an exponential equation. I'm going to go with the first equation into a ln, see where that takes us. So if we're going to turn this into a ln equation, we're going to need to get the exponential term to be on its own on one side of the equation. So if we rearrange this, we're going to get 9x minus 5. So e to the y equals 9x minus 5. Then we can turn this into a ln equation. So power equals log base e, which we write as ln of 9x minus 5. That's quite nice because we can substitute in for the y in equation 2. So we're going to have ln of 9x minus 5 minus ln of x plus 4 equals 2. Subtraction between the ln's means we can divide inside. X plus 4 equals 2. Now we can go back to an exponential equation in order to solve it. So we are base e, so it's going to be e squared equals 9x minus 5 over x plus 4. Multiplying up, e squared x plus 4e squared equals 9x minus 5. We're going to want to get our x terms on one side, so e squared x minus 9x equals minus 4e squared minus 5. Take x out to get e squared minus 9 in the bracket. Now I don't like having these two negative terms at the top, so what I'm going to do here is I'm going to make them both positive, and I'm going to flip around the e squared minus 9 to make it 9 minus e squared. So it's like I'm multiplying the top and the bottom by -1, which just has the effect of changing the signs of everything in both the numerator and the denominator. Okay, so now we can go back, make sure we remember to find our y value. So y is ln, so this is going to be a little bit messy. 9 lots of x, so I'm just going to take that 9 straight in, so 36e squared plus 45 over 9 minus e squared minus 5. We could put that as a single fraction by taking away 5 times 9 minus e squared over 9 minus e squared. Well, let's just go ahead and do it, I guess. The question, if it was an exam question, would probably specify what form it wanted the final answer in. So we've got 36e squared plus 45. We're then going to have to take away, so what we'd basically be doing here is multiplying the 5 by both the top and the bottom by the denominator, so that the denominators are the same, and we can then just subtract. So we're going to minus, oh, it actually works out quite nicely, minus 45 and then plus 5e squared, careful with that minus times a minus, all over 9 minus e squared. Simplifying a little bit there, 45's cancel, 36e squared plus 5e squared, 41e squared. Okay, that was worth doing in the end. That looks significantly nicer than what we started with. And then we have our 2 solutions. That is the final question. So the next video in the series is going to be looking at the using logs to linearize exponential and polynomial functions. So that's producing a straight line graph using logs and the kinds of questions that we can get around that. And then finally in this series will be the modelling with exponentials and logs, and that will also bring in some of the differentiation of the exponential function as well. So if you found the video helpful, please don't forget to hit the thumbs up button, and also subscribe if you'd like to see more, and I'll see you in the next one. Bye.